Welcome! In this session, we'll explore LeetCode problem number 1433, titled Check if a string can break another string. This problem challenges us to determine whether one string can break another based on specific rules. It's a fascinating exercise in string manipulation and algorithm design. Let's dive in and unravel the solution together. In this problem, you are given two strings, s1 and s2, both of the same length, n. The goal is to determine if one string can break the other. Here, breaking means that if you rearrange the characters of both strings in lexicographical order, every character at index I in the first string is greater than or equal to the corresponding character at index I in the second string. If this condition is satisfied for s1 breaking s2, or for s2 breaking s1, then the output should be true. Otherwise, the result is false. The input consists of two lowercase English strings of equal length, and the output is a Boolean value indicating whether the condition is met for either string breaking the other. To better understand the problem, let's look at the first example. Suppose S1 is ABC and S2 is Zaya. Sorting S1 gives ABC, and sorting S2 gives AXI. Now, we compare the characters at each index. At index 0, A is less than or equal to A. At index 1, B is less than or equal to X. At index 2, C is less than or equal to Y. Since all characters in S1 are less than or equal to the corresponding characters in S2, we can say that S1 can break S2. Therefore, the output in this case is true. Now for the second example, consider S1 as AB and S2 as ACD. Sorting S1 results in AB, and sorting S2 gives ACD. Comparing the characters at each index, we see that at index 0, A is less than or equal to A. At index 1, B is less than or equal to C. However, at index 2, E is greater than D. This means that not all characters in S1 are less than or equal to the corresponding characters in S2. So, S1 cannot break S2. Let's now check if S2 can break S1. Comparing their sorted versions, at index 0, A is greater than or equal to A. At index 1, C is greater than or equal to B. However, at index 2, D is less than E. Since not all characters in S2 are greater than or equal to the corresponding characters in S1, S2 cannot break S1 either. Therefore, the result for this example is false. For another example, consider S1 as LeetCode and S2 as interview. Sorting S1 gives DLOT, and sorting S2 results in INTRV. Comparing the characters at each index, we have C is less than or equal to E, D is less than or equal to E, E is less than or equal to I, and so on. For all indices, the characters in S1 are less than or equal to the corresponding characters in S2. This means that S1 can break S2, and the output for this example is true. Now let's discuss some important constraints and edge cases for this problem. The length of both strings, n, is the same, and it can range from 1 to 100,000. Both strings consist only of lowercase English letters. Some interesting edge cases include when n equals 1, where the strings are single characters. In this case, the result is always true because any character can break another. Another case to consider is when the two strings are identical. Here, the result is also true since a string can always break itself. If the strings consist of completely different sets of characters, the result depends entirely on their sorted order. Finally, for very large inputs, with n at its maximum value, efficient sorting and comparison are crucial to ensure the solution meets the time constraints. To solve the problem of determining if one string can break another, we first need to understand the concept of breaking. If string X can break string Y, this means that, after sorting both strings, every character in X is greater than or equal to the corresponding character in Y at every index. A straightforward but computationally expensive way to approach this is through a brute force method. Here, we would generate all possible permutations of both strings and then check if any permutation of S1 can break any permutation of S2, or vice versa. However, this approach has a time complexity of O(n). (2), where n is the length of the strings, because generating permutations involves factorial operations. This makes it completely impractical for larger strings, as the number of permutations grows exponentially. Due to these limitations, we need a more optimized approach to handle the problem efficiently. A much better way to solve the problem is by using an optimized approach based on sorting. The intuition here is that sorting both strings gives us a direct way to compare their characters at corresponding positions. Once the strings are sorted, we can simply check two conditions: whether all characters in the sorted version of S1 are greater than or equal to the corresponding characters in S2, or whether all characters in the sorted version of S2 are greater than or equal to the corresponding characters in S1. If either of these conditions holds, then one string can break the other, and we return true. Otherwise, we return false. This approach is efficient, with a time complexity of O(n) log n, due to the sorting operation, and it only requires O(n) additional space for storing the sorted strings. This makes it well suited for the problem's constraints. The key realization that simplifies this problem is that sorting the strings reduces the complexity of checking the breaking condition. Instead of exploring all possible permutations, sorting allows us to directly evaluate the relationship between the two strings. This insight is crucial because it transforms the problem from an infeasible factorial time complexity to a much more manageable O(n) log n. Sorting not only improves efficiency but also simplifies implementation, as we only need to compare characters in the sorted strings. While the brute force method theoretically examines every possibility, it is computationally prohibitive. The sorting-based solution is a smart trade-off, balancing efficiency and clarity. Additionally, while frequency-based methods like using character counts could be an alternative, they introduce more complexity without offering a significant advantage over sorting. For these reasons, sorting is the most practical and optimal choice for this problem. Ultimately, our final strategy revolves around the sorting-based approach. This method is efficient, straightforward, and aligns perfectly with the problem's requirements. By sorting the strings and comparing their characters, we avoid unnecessary computations and arrive at a deterministic solution. It simplifies the process while adhering to the constraints, making it the ideal approach for solving this problem. The simplicity, combined with its efficiency, ensures that it is both easy to implement and robust enough to handle typical input sizes effectively. The problem asks us to determine if one string can break another. To clarify, a string X can break another string Y if, after sorting both strings, every character in X is greater than or equal to the corresponding character in Y at each index. Our goal is to decide if string S1 can break string S2, or vice versa. To solve this, we start by validating the input. Both strings must be non-empty and of the same length, otherwise, the function should return an error or false. Next, we sort both strings. Sorting them ensures that the characters are in ascending order, making it easier to compare them index by index. This preprocessing step has a time complexity of O(n) log n, where n is the length of the strings. By sorting, we lay the groundwork for an efficient comparison in the next steps. Once the strings are sorted, we move on to comparing their characters. To do this, we initialize two flags, S1 breaks S2 and S2 breaks S1, both initially set to true. These flags help us track whether one string can consistently dominate the other. For each index I, we compare the characters at that position in the sorted strings. If a character in sorted S1 is less than the corresponding character in sorted S2, we know that S1 cannot break S2, so we set S1 breaks S2 to false. Similarly, if a character in sorted S2 is less than the corresponding character in sorted S1, we update S2 breaks S1 to false. If both flags become false, we can immediately return false because neither string can break the other. Finally, if one of the flags remains true, we return true. This approach leverages the sorted order to simplify the problem, avoiding the need for more complex operations like counting character frequencies. Additionally, early termination helps optimize the solution by reducing unnecessary comparisons. It's also important to consider edge cases, such as strings with the same characters in different orders, which become identical after sorting and can break each other. Another edge case is invalid inputs, like strings of different lengths. Another interesting case arises when one string is lexicographically smaller or larger than the other. For example, if S1 is AAA and S2 is ZZZ, the sorted order makes it clear that S2 will always dominate S1. To efficiently handle these scenarios, we rely on sorted lists. By sorting the strings, we enable direct index-by-index comparisons, making the problem much simpler. In terms of complexity, the sorting step dominates the runtime, taking O(n) log n. The subsequent character comparisons are linear, O, n, so the overall time complexity remains O, n log n. For space complexity, we use additional memory to store the sorted lists, which requires O, n, space. Together, these complexities make the algorithm efficient and scalable for moderately large inputs. Now, let's consider an example to see how this works in practice. Imagine the input strings are S1 equals ABC and S2 equals Zaya. First, we sort both strings. For S1, the sorted result is B, C, and for S2, it's X, Y. Next, we compare their characters index by index. At index 0, both strings have the character A, so neither flag changes, and both remain true. At index 1, sorted _S1 has B while sorted _S2 has X. Since B is less than X, S2 breaks _S1 is set to false. Finally, at index 2, sorted _S1 has C and sorted _S2 has Y. Again, C is less than Y, so S2 breaks _S1 remains false. At the end of the comparisons, S1 breaks _S2 is true, and S2 breaks _S1 is false. This means S1 can break S2, so we return true. This example demonstrates how the algorithm efficiently determines the result using sorted lists and simple comparisons. This solution solves the problem by leveraging sorting and a comparison-based approach. First, both input strings S1 and S2 are sorted in ascending order. Sorting allows us to compare the characters of both strings index by index in a straightforward manner. Once sorted, the algorithm initializes two Boolean flags, S1 breaks S2 and S2 breaks S1, to track whether either string can break the other. It then iterates over pairs of corresponding characters from the sorted strings using the zip function. During this iteration, if at any index the character in S1 is smaller than the character in S2, it sets S1 breaks S2 to false since S1 can no longer break S2. Similarly, if the character in S2 is smaller than the character in S1, it sets S2 breaks S1 to false. After completing the iteration, the function returns true if either S1 breaks S2 or S2 breaks S1 is true, indicating that one of the strings can indeed break the other. This implementation is efficient with a time complexity dominated by the sorting step, which is O, n log n, where n is the length of the strings. It also handles all edge cases, such as strings with equal characters or strings of varying arrangements, ensuring correctness in all scenarios. Here, we define the checkIfCanBreak method, which takes two strings, S1 and S2, as input. The goal is to determine if one string can break the other. To start, we convert both strings into character arrays, S1 sorted and S2 sorted, and sort these arrays in ascending order. Sorting is important because it allows us to compare the corresponding characters of both strings in a systematic way. Next, we initialize two Boolean variables, S1 breaks S2 and S2 breaks S1, setting both to true. These will help track whether S1 can break S2 or vice versa. Then, we use a for loop to iterate through the characters of the sorted arrays. At each index, we compare the characters. If a character in S1 sorted is smaller than its counterpart in S2 sorted, we set S1 breaks S2 to false, meaning S1 cannot break S2 at that position. Similarly, if a character in S2 sorted is smaller than its counterpart in S1 sorted, we set S2 breaks S1 to false. This comparison continues for all indices of the arrays. Finally, after the loop completes, we return the result of the logical OR operation between S1 breaks S2 and S2 breaks S1. If either variable remains true, it means one string can break the other. This approach ensures that we efficiently evaluate the relationships between the two strings after sorting, and the solution leverages sorting and a single pass through the arrays to achieve an optimal time complexity. This concludes the implementation of the checkIfCanBreak method. Here, we start with the first example where S1 is ABC and S2 is Zaya. The first step is to sort both strings alphabetically. Sorting S1 gives us a B and C, and sorting S2 gives us a X, Y. Once sorted, we initialize two flags, S1 breaks S2 and S2 breaks S1, both set to true. These flags are used to track whether one string can consistently break the other. Next, we iterate through the sorted versions of both strings, comparing characters at each index. At index 0, both characters are a, so neither S1 nor S2 can establish dominance. At index 1, we compare B from S1 with X from S2. Since B is less than X, S1 underscore breaks underscore S2 is set to false. Finally, at index 2, C from S1 is compared with Y from S2, but no further flag changes occur because C is not less than Y. As the iteration concludes, no further changes are made to the flags. Now, we evaluate the result by checking if either of the flags is still true. In this case, S1 underscore breaks underscore S2 is false, but S2 underscore breaks underscore S1 remains true. Therefore, the result of the condition S1 underscore breaks underscore S2 or S2 underscore breaks underscore S1 evaluates to true, and the function outputs true for this example. Moving to the next example, we have S1 as AB and S2 as ACD. As before, we start by sorting both strings. Sorting S1 gives a B, E, and sorting S2 results in a C, D. Again, we initialize the flags S1 underscore breaks underscore S2 and S2 underscore breaks underscore S1 to true, preparing to iterate through the sorted strings. During iteration, we compare characters at each index. At index 0, both characters are a, so the flags remain unchanged. At index 1, B from S1 is compared with C from S2. Since B is less than C, S1 underscore breaks underscore S2 is set to false, while S2 underscore breaks underscore S1 remains true for now. At index 2, E from S1 is compared with D from S2. Here, E is greater than D, so S2 underscore breaks underscore S1 is set to false. At this point, both flags have been set to false as neither string can consistently break the other. Evaluating the result, the condition S1 underscore breaks underscore S2 or S2 underscore breaks underscore S1 evaluates to false. Therefore, the function outputs false for this example. Next, we consider the third example where S1 is XYZ and S2 is of. As before, we start by sorting both strings. Sorting S1 gives X, Y, Z, and sorting S2 gives U, V, W. Once sorted, we initialize the flags S1 underscore breaks underscore S2 and S2 underscore breaks underscore S1 to true. Now, we compare characters at each index. At index 0, X from S1 is compared with U from S2. Since X is greater than U, S2 underscore breaks underscore S1 is set to false, while S1 underscore breaks underscore S2 remains true. At index 1, Y from S1 is compared with V from S2. The same pattern continues as Y is greater than V, so S2 underscore breaks underscore S1 remains false. Finally, at index 2, Z from S1 is compared with W from S2. Again, Z is greater than W, and no changes are made to the flags. With the iteration complete, we evaluate the result. Here, S1 underscore breaks underscore S2 is still true, while S2 underscore breaks underscore S1 is false. Therefore, the condition S1 underscore breaks underscore S2 or S2 underscore breaks underscore S1 evaluates to true. The function outputs true for this example, as S1 can break S2 under these conditions. This concludes the walkthrough of the solution for the problem, highlighting how sorting and flag checks allow us to determine if one string can break the other. The time complexity of this solution can be understood by analyzing its key components. First, we have the sorting operations on the input strings. Sorting a string of length n has a time complexity of O, n log n, and since we are sorting two strings, this step contributes a total of O, n log n. Next, we iterate through the sorted strings using the zip function. This iteration, which processes both strings of length n, has a time complexity of O, n. Within this loop, we perform constant time comparisons between character pairs, like C1 C2 and C2 C1. These comparisons are repeated for each pair of characters, contributing an additional O, n. When we combine these factors, the sorting step dominates the overall time complexity, meaning the final time complexity is O, n log n. Now let's discuss space complexity, which evaluates the extra memory used by the solution. The sorted function produces new sorted lists for both input strings, and this requires O, n, additional space for each string. Therefore, the total space consumed for sorting is O, n, plus O, n, which simplifies to O, n. Beyond sorting, the solution uses a few temporary variables like S1 underscore breaks underscore S2, S2 underscore breaks underscore S1, C1, and C2, all of which occupy constant space, or O1. The input strings themselves are not modified, so they don't contribute additional space beyond their original size. As a result, the overall space complexity is dominated by the sorting step, leading to a final space complexity of O(n). When comparing this solution to a brute force approach, the efficiency becomes clear. A naive method would involve generating all permutations of one string and comparing each permutation to the other string to check the break condition. For a string of length n, generating all permutations has a time complexity of O(n), which is exponential and impractical for large inputs. In contrast, the current solution utilizes sorting to simplify the problem into a single comparison pass, reducing the time complexity to O(n log n). This is a significant improvement. For best, average, and worst case scenarios, the sorting step always dominates with its O(n log n) complexity. Even in the worst case, where the break condition is determined at the last character of the strings, the overall complexity remains O(n log n). Finally, the mathematical reasoning behind the big O complexities highlights why this solution is efficient. Sorting governs the time complexity because O(n log n) grows faster than O(n), making it the dominant factor. The iterations and comparisons that follow sorting are linear, but their contribution is overshadowed by the sorting step. On the space complexity side, the primary contributor is the additional memory required for sorting, which scales linearly with the input size as O(n). Altogether, the solution strikes an excellent balance between efficiency and scalability, with a time complexity of O(n log n) and a space complexity of O(n), making it far superior to the brute force alternative. Here, we'll discuss some common mistakes to avoid when solving this problem. First, not sorting the strings is a frequent error. Sorting is crucial because it allows us to compare characters in a consistent order. Without sorting, the comparisons between characters would be misaligned, and the logic to determine whether one string can break the other would fail. Next, there's the misunderstanding that both strings must break each other. This is incorrect. The problem only requires one string to break the other, so focusing on mutual breaking leads to unnecessary complexity. Another mistake is overlooking edge cases. For example, strings with duplicate characters, like AAA and AAA, or strings of length 1, are easy to miss during testing. Ensuring you account for these scenarios is key to building a robust solution. Another common issue is incorrect character comparison. When comparing characters, we rely on their ASCII values to maintain lexicographical order after sorting. Mistakes here can occur if comparisons are handled manually instead of leveraging the properties of sorted strings. Additionally, inefficient implementations can arise when nested loops or redundant data structures are used. For this problem, sorting the strings followed by a linear comparison is sufficient. Extra loops or data structures not only complicate the solution but also increase the time complexity unnecessarily. Keeping the implementation clean and efficient ensures that the solution runs optimally. Now, let's look at some important insights for interviews. Sorting is the central insight for this problem, as it simplifies the solution to a linear comparison after the initial O(n log n) sorting step. Testing edge cases is another critical aspect. Strings of length 1, strings with repeated characters, or completely disjoint character sets are examples that must be considered. Discussing alternative approaches, such as using histograms to count character frequencies, can impress interviewers by showing an understanding of different methods and their trade-offs. Finally, be prepared to explain the time complexity. Sorting both strings is O(n log n), and the comparison is O(n), making this approach efficient overall. You could also relate this problem to similar ones, such as LeetCode 937, where strings are sorted based on custom rules, or LeetCode 242, which involves sorting to test if two strings are anagrams. Finally, let's explore some alternative approaches. A histogram approach involves counting the frequency of each character in both strings and comparing cumulative counts. This avoids sorting and runs in O(n) time, but it requires additional space for the frequency arrays. Another option is using two pointers without sorting. Here, you manually compare characters one by one while maintaining pointers for both strings. This approach has its own challenges, as it's harder to implement and debug, and sorting is typically more intuitive for this problem. Lastly, there's the brute force method, where you compare every character in one string with every character in the other using nested loops. While this demonstrates the problem's mechanics, it's highly inefficient with O(n)² complexity and is primarily useful for understanding why optimized solutions are essential. Great job! To recap, we solved the problem check if a string can break another string by utilizing sorting and string manipulation techniques. Remember, this type of problem is a great way to sharpen your skills for interviews. Thank you for joining, and don't forget to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!